first order logic. And by the way, I'm going to go in both directions. Right now we're going up to full first order logic, and then I'm going to go down to simpler logics. But what about full first order logic? We started with QK, QD extends that, QT extends that, and we've seen enough non-provable things to verify that these are proper extensions. What more do we need to get full first order logic? Anybody want to guess at an axiom? Okay, so the question is, what do you need to get the Henkin completeness proof to actually work in its usual way? Okay, we've got Henkin witnesses for existential statements, but if a universally quantified formula fails at a world, you'll have a counter instance, not at that world, but at an accessible world. So you've changed worlds. And what we need is some way of those witnesses accumulating. So if you're at this world and this universally quantified formula fails, you move to another world, you get an instance where that fails. But now you have this other universally quantified formula, so you have to move to a different world to get a counterexample for that. And what you're doing is creating a chain of worlds. What you need is some way of taking a limit of that chain so you can accumulate everything you've done. The trouble is when you move from a world to an accessible world, formulas get lost. Remember, you move from gamma to gamma sharp. You drop some formulas. What you need is formulas not to get lost. If gamma forces x, if x is true at gamma, and you move to an accessible world delta, you'll still have x. So you need something to guarantee these formulas accumulate as you keep moving from world to world. So that's the essential difference between the modal case and the quantifier case. Semantically, but here, modal operators always do something. If you put a box on a formula, it has an effect. Quantifiers don't always do something. There are vacuous quantifiers. They don't do anything. That's exactly what you need. Vacuous quantification, phi implies for all x phi, provided x is not free in phi. It's a vacuous quantifier. For all x phi, it will be, for all intents and purposes, the same as phi. So this is the axiom you need to add. If you add this to QK, QT, QD, you get full first order logic. The corresponding modal axiom, of course, would trivialize modal logic. So why does it give you the accumulation property? Well, that's very simple. Suppose gamma forces phi and gamma is related to delta. Well, this is from the slide that I left out. What it says is if delta is accessible from gamma, then anything that's, then what you want is all the universally quantified things here instantiated with things from the domain of delta are here. Well, since x is not free in phi, and phi is, I assumed, something in gamma, and we have this as an axiom, this is vacuous quantification, for all x phi will be in gamma. When you move to delta, you lose the quantifier, but it didn't do anything anyway, so you have phi in delta. It's exactly this that gives you the accumulation you need. So with that, the usual Henkin completeness proof works. Do it in, say, QT, plus vacuous quantification. Construct the canonical modal model, the canonical possible worlds model. If x is not provable, there'll be some member where it does not occur. enumerate all the universal quantifiers. This begins to look like the Henkin completeness proof. But instead of adding them to your set, what you're doing is moving from world to world to world. These are all the universally quantified ones. Okay, you're at this world where you don't have X. Move to a world that falsifies Q1. From there, move to a world that falsifies Q2, and so on. And then take a limit, which you can do now. So this is the sequence that successively falsifies things. Okay, that defines that. Then you can take a limit, and that will be your proper counter model. So I'm leaving the details out here, but so in effect, vacuous quantification is exactly the thing you need. So as I said, this is the usual construction, but kind of in disguise. And you know, vacuous quantification seems like a kind of sometimes trivial, sometimes a nuisance, but it's the essential thing here. Okay. Other proof procedures. I showed you axiom systems. If you've seen tableau systems for modal logics, you should be able to invent them for these quantified logics. Let's see. I'm not going to show them here, but the paper is on my website if you want to see them. But it's exactly what you would think. Take the modal rules. Every place you do something with a box, do the same thing with a universal quantifier. You'll get tableau systems for these logics. And what that gives you along the way is you take one way of showing the modal logic K is decidable, is to show any tableau construction has to terminate, and either you'll have a proof or you'll have enough information to get a counter model. Exactly the same thing works for QK, so that's a decidable logic. This is not quite true. I don't know if it's true. I don't know about QT, but I said here it holds for QD, but in fact I don't know about QD either. I don't know at what point you get to undecidability coming along. You can use modal tableaus to prove interpolation theorems. Well, you can use these quantifier tableaus to prove interpolation theorems here. So each of these sublogics of first order logic has interpolation, the interpolation property. Okay, so we've gone up to classical logic, full classical logic. What about going in the other direction? Well, you know, what's simpler than K? I don't know. Generally these days people tend to concentrate on normal modal logics, but there are families of logics weaker than normal modal logics. The first one that comes along is what's called the regular logics. For K, you have this rule of necessitation. Instead we'll drop that and use this, which is called the rule of regularity. It's strictly weaker than necessitation. We'll still keep the axiom box X implies Y implies box X implies Y. If you have necessitation, this is a derived rule. But if you have this, that is not a derived rule. But the derivation will use that distributivity axiom. The weakest regular modal logic is called C. It's the analog of K. So this is an axiomatization of C. So the difference is in this rule here. In C, you can still prove box distributes over an and, but there are no theorems that say something is necessary. In particular, truth is necessary as a provable thing. Well, if in fact, if you had this, C would collapse to K. Because if X is a theorem, so is T implies X. By regularity, so is box T implies box X. If you had box T, you'd have box X. You'd have the usual rule. But that's not a proof that this is not provable. We need the semantics for that. Among his early papers, Saul Kripke gave us semantics for these regular logics. The possible worlds and accessibility and truth of the world generally are the same, but you have this collection N. He called them, he worked with the complement of it and called them queer worlds. Here I'm working with this and calling them normal worlds. If you're a Graham Priest fan, you'd be talking about non-standard or non-classical worlds or something like that. But N is supposed to be the worlds where things behave the way you're used to, and everywhere else they behave peculiarly. So you have this set N, and if N is all of G, this will just be your standard K models. But the thing is about how box behaves. So this says if you're at a normal world, box behaves normally. It's true if the unboxed thing is true at all accessible worlds. If you're at a non-normal world, well, very simply, everything is possible and nothing is necessary. You don't even have to look at the structure of it. It's just all possible statements are true, all necessary statements are false. One can prove soundness and completeness for these by absolutely straightforward variation of the usual soundness and completeness proofs. And one can give tableau systems for them. Again, since I didn't show you the tableau systems for normal logics, I won't show you these either, but they're again straightforward. So what about quantifier analogs for that? What you would do is drop universal quantification and put this in. So this is QC, it's a quantified analog of C. You can define QC models in the expected way. You have all of the structures of the QK models, except you also have this set of normal worlds. So the conditions would be at normal worlds, it's the same definition we had before. And at non-normal worlds, all existential statements are true and all universal statements are false. No boxes, but all diamonds. So here's an example. This isn't an example where I'm going to do anything with it, just to show you what it's like. So A and B are just predicate letters here, and T is a tautology, just any tautology will do, just let's say it's this one. So here's a three-world model. The arrows indicate accessibility, and you have reflexivity, so each world is accessible to itself. And I've shown you the domains of each world. The blue ones are normal, and the whatever that is, magenta, are not normal. Okay, since T of X is a tautology, T of A is true up there. T of A and T of B are true here, and also true here. That tautologies evaluate without bothering about the quantifier rules. do something? Okay, so up there at the top, for all x, t of x is true because all instances are true at each accessible world. That's here and here, and both you have t of a and t of b. Down here, for all x, t of x is true because all instances are true at all accessible worlds because this is the only accessible world. Over here, not for all x, t of x is true because it's not a normal world, so universal statement quantified things are not true. Over here, this implication is true because the consequent is true. Up there, let's see, why is that implication true? Because the consequent is true. Down here, this implication is true because the antecedent is false. I never said be held of anything. All right, that was just to give you some feeling for how these things are evaluated. One can go a little further in this direction. You can add this to the regular version. You can add this. For the D version, on the semantics you assume seriality. For the T version, reflexivity. But again, you allow non-normal words. The soundness and completeness proofs carry over, no problem. And there are tableau systems for these, and there are interpolation theorems for these. So we've got this structure so far. Q is first order classical logic, and then various sublogics of it, the lattice of them. Those are the analogs of the normal ones. These are the analogs